Okay. Now, when we graph these things, I graph it with patterns. I very rarely will pick up my calculator. In pre-calc, most of the time we're sketching. And if you kind of notice, your sketches need your 4 quadrant angles here, and we need to know what our height is in the Y. We don't have to know all the little 45, 30, 60 angled degrees in the middle. We don't have to know those unless that's where your quadrant is going to fall. If we compress these or we stretch these. So we're going to start with your unit circle. What's the radius on my unit circle? 1. So we go out 1, we go up 1, we go over 1, and we go down 1. Now, picture this. I cut a piece of string. I take the string, I start here, I wrap it around my circle. On my string, I make a tick mark at 90 degrees, one at 180, one at 270, back here. I take this string and I unravel it. I put it here where my origin is, and I roll it out like this. So my tick mark says 90, 180, 270, 360. All right, I just unraveled my circle. Now, I'm looking at my sign. My sign is which value, my X or my Y? My Y. So, God bless you. At the 0 degrees, what is the sign of 0? Follow your Y's. 0. At 90 degrees, what is the sign of 90? 1. At 180, what is the sign? 0. At 270, and back around. Okay, so now, Brenda knows my pattern here. We say 0, 1, 0, -1, 0. This is my cycle. So if I needed to do this cycle again, I would make myself 4 new quadrants, and I would say 0, 1, 0, -1, 0. I would make another cycle. Do you see my cycle? It's a pattern. It repeats itself. When I go into my negatives, I just go backwards. Keep this curve coming down here. -1, 0, 1, 0, -1, 0, 1, 0. See the curve? It just keeps on going. Now, when you talk the domain of your sine curve, it's the domain of the entire sine curve, not just the window that I need to look at. Obviously, we have to have a spot where we start and we begin, right? Where we end and we start. So we have to have a cutoff. That's not my domain of my curve. My domain of my curve for the sine curve is what? What's the domain for your sine curve? All real numbers. Good. It just so happens that maybe I just graphed from here to here, but my curve is still all real numbers. What's the range of my sine curve?
-1 to -1.
Very good. -1 to 1. And we use hard brackets because we use the 1 in the -1. Now, interestingly enough, at your 90, from 0 to 90 is quadrant 1. From 90 to 180 is quadrant 2. From 180 to 270, quadrant 3. And 270 to 360, quadrant 4. Now we can trace where your sign is positive and negative. In quadrant 1, it's positive. Look where it is, above here. In quadrant 2, it's positive. In quadrant 3, negative. In quadrant 4, negative. So it is a reflection of, not a reflection, but the fact that we unraveled it onto your graph, it has to match up to what you originally had. Now, if I measure this, our normal format is A sine BX. Without any phase in this right now, we're just going to be just a normal curve. A is your amplitude. Your amplitude is the measurement from the resting point to the top or the bottom of your curve. So from the resting point here to the top, this is my amplitude. From the resting point to the bottom, there's my amplitude. Your amplitude is always positive because it's a distance. It's like the height of my curve. You guys that play music, right? When you say turn up the amps, what do you do? When you say turn it up, what do you do?
I turn it down. I turn it down.
What do you turn up? The volume. You turn up the volume. So if I say amp it up, you're increasing the amps on this, right? So therefore, your curve is going to go like this. It's going to change the amp. This is going to change the volume. If you've ever seen like your voice curves, did anybody ever watch like when you say something and your voice curves go like this? Or you have music and you see there's sinuses or something like that. There's sinoids or something.
Like whales, with the whales.
With the whales too. Sonar, they run those things down there. And then you can tell how they are. Now, when you change the pitch of something, that's the frequency. So if I change the pitch and make it high pitched, I have more of these curves. That's a frequency. If I spread it out, my pitch is really, really low, right? So the frequency, and these work off of real curves. These are real sine curves. And they work off of your radio waves, your sonar waves, your seismograph waves. Those are all trig curves in here.
Which one is it called? Wait, the seismograph is one in hospital?
A seismograph, that's your earthquakes.
Oh, yeah.
Yeah.
What's it called? What's the machine called?
Like the EKG?
Yeah, there you go.
Yeah. I'm not so sure like how that registers.
Are those time codes for it?
I'm not really sure, but I know they do go up and down.
Yeah.
I'm not sure of the pattern of those exactly. Yeah.
They don't go like below.
Yeah.
They stay above. Yeah. But their resting line should be higher up. Probably back. Okay. Guys, can we stick with this for a few minutes? All right. Now, if we want to change this at all, we can change our amplitude, like we amped it up here. So say I change this to a 2. If I made this be -2, my amplitude is still 2. But what does the negative do in terms of a transformation?
Oh, it goes down.
It makes it go down. It's the reflection where? Over the x-axis. So this negative is going to say, don't go up, go down. Whoops, go down first, then go up. See, it's a reflection of this blue one, the original blue one. So our amplitude is still positive. It's still going to be a +2, +1, +3. The negative causes a reflection. That's your transformation. Yeah.
Wouldn't it go down to the
It would go down to -2. Yeah, I was just making like that. It'll just go underneath it. It'll do the opposite. Back of this red one, I should have said. Yeah. Then I got going crazy first time. All right. So now, what else can I say? Your frequency. Your frequency is the B. Your frequency tells you this. How many complete cycles in 2 pi? And I want you to write that down. How many complete cycles?
That's frequency.
That's frequency. In 2 pi. How many degrees in 2 pi? 360. So isn't 360 our unit circle? 360 degrees? Isn't that our unit circle? So on our normal sine curve, how many full cycles do we make in 360? 1. That's where this 1 comes from, right there. Okay. Now, if we'll humor Brendan. If we make this be 2, that means I want 2 cycles in 360. Therefore, how long does it take to complete 1 cycle? Pi. Very good. So your period is 2 pi over b. 2 pi over 2 gives me pi. If you have trouble in pi, think of degrees. if I'm going to complete 2 cycles in 360, it's going to take me half of that to do one of them. So my period would therefore be 180, and 180 is the same as pi. Now, watch what this pattern does for us. If I want to change this to 2 here, at the 180, I have to have gone around 360. And then from here to here, another 360. How many quadrants in 360? 4 quadrants, right? I need to complete 4 quadrants in this short time. So I take this and I increment this into 4 equal parts. So can I take half of this one, half of this one? So at 90, half of 90 is 45, right? So watch my pattern. I follow this pattern. 0, 1, 0, -1, 0. I don't really care about my in-betweens. All I care about is my quadrants, my major points. My quadrants and my zeros over here get my mins and my maxes and my intercepts. That's all I care about. I need a min, I need a max, and I need an x-intercept. That's what my 4 quadrants gives me. Now, I'm going to do it again here. I'm going to take this and break it into 4 equal parts. And go 0, 1, 0, -1, 0. So now, don't I have 2 complete sine curves in 360? Is this called a horizontal stretch or a shrink?
No, if it's more cycles,
Oh, no, it's shrink.
It's shrinking. It's kind of a little bit reversed than the other ones because it's shrinking this. It's like an accordion. It's compressing this in. What would my stretch look like, do you think?
that's what we do my time.
Yeah.
It's like an accordion.
So, Ricky, what value would you put in here to stretch this out? Half. They're helping you out. So now, if I want to go half of my curve in 360, here's my 360, half of my curve. How long is it going to take to complete the whole entire curve? Another 2 pi, right? 720. So I've got this piece half, and this piece half, and this will be here at 4 pi. Because watch, 2 pi divided by 1/2 says keep, change, flip. This gives me 4 pi. So if I do half of my curve in 360, I got the other half in another 360. Think of it logically first. Give me a few minutes, guys. I got a couple more minutes, right? All right, a couple more minutes. Now, let's hit the cosine curve real fast.
Does not look like
Cosine, yeah, it kind of does. Here's my unit circle. So what values are we using now for cosine? The x, good. So let's pull out your x values. Start at the 0. What do we pull out? 1, 0, -1, 0, that's 1. So watch. 1, 0, -1, 0, 1. This is 1 cycle. Now I can go reverse. Just bring this back down to -1, 0, 1. What's the domain for this guy? All real numbers. Even though we're just in this window, we're still all real numbers. What's the range? Good, -1 to 1. Now, if you notice, here's your sine curve. Let me put your sine curve here. Guys, stop. It's kind of fast. Just moved over. How many degrees should I shift it over? 90. 90. Now, think of your 30, 60, 90 triangle. Isn't the sine of 30 the same as the cosine of 90? Right? And look where these are crossing. Halfway between 0 and 90, what angle is this where the sine and the cosine are the same? 45. So your sine and your cosine are the same curves, just a little shift of 90 degrees. Because there are co-functions in this. Okay, so it still has the same attributes. It still has your same pieces there.